Welcome back to the Deep Dive. Today, we are taking a massive leap out of the sterile environment of the operating room and diving headfirst into the messy, dynamic reality of postoperative life.
I like that. The messy reality.
It is. Our mission today is a full-spectrum deep dive into how orthopedics moved from relying on static post-op x-rays, which, let's be honest, tell you what the joint looks like when it's standing still.
And only when it's standing still.
Right. To capturing truly dynamic, in vivo tracking of total joint replacements in motion.
It's really the difference between looking at the blueprint of a skyscraper and then monitoring its structural integrity during a Category 5 hurricane.
That's a great analogy.
Surgery, even a perfectly executed total joint replacement, or TJR, is only half the battle. For decades, we were performing this beautiful mechanical work without truly understanding the three-dimensional motion, the kinematics, once the patient actually used the joint.
You mean once they're out in the real world, under real-world loading?
Exactly. And that lack of understanding was a fundamental failure point in optimizing implant design.
So today we're discussing the evolution of mobile fluoroscopy, and we're going to focus on the sophisticated work done at the University of Tennessee, Knoxville. This all culminates in the patented design known as the Tracking Fluoroscope System, or TFS.
For almost 20 years now, conventional fluoroscopy has been, essential for in vivo analysis of postoperative TJR results, especially in the knee. The concept was straightforward. Capture digital X-ray frames of the joint moving.
But the real breakthrough came when we realized we could computationally fuse those digital frames with precise 3D graphical models of the joint implants themselves.
That fusion is everything.
That computational fusion is the absolute key. Because once you have that high-fidelity 3D motion data, the kinematics, you are no longer just measuring position. You can apply the concept of inverse dynamics.
And this is where the surgeon becomes an engineer. Inverse dynamics uses the observed motion, the kinematics, combined with patient-specific data like mass and acceleration to calculate the actual measurable forces and moments occurring within the joint structure.
So, for example, the precise compressive and shear loads acting between the femoral component and the tibial tray in a knee replacement during a deep lunge.
Exactly. They're not just confirming gross alignment and component position on a static image anymore.
No, you're calculating the actual stresses and strains being placed on the components, the real forces the joint interface experiences during, daily activities.
Precisely. And that is the clinical payoff. That detailed force system data has particular and, frankly, profound relevance to the long-term performance of the joint interface materials.
When we talk about implant longevity, we're talking about failure modes.
And the dominant one remains polyethylene wear. If we don't understand the true forces and micromotions causing that wear under dynamic loading, we are merely guessing at how to optimize the design of the polymer insert and the metal articulation surfaces.
But doctor, before the TFS, there was this technical brick wall we kept slamming into. The limitation of conventional fixed C-arm fluoroscopes in capturing truly natural, unrestricted motion. That fixed constraint was the problem that needed solving before any of this force calculation could happen effectively.
It was the single biggest hurdle.
Okay, so let's unpack that frustration. Let's dig into the legacy C-arm system. It's a fantastic tool, intraoperatively, we all know that. But why did it become an immediate failure when we tried to move it to the biomechanics lab to analyze activities like walking or deep knee bends or just sitting and rising from a chair?
The failure is inherent in the design. You're trying to use a static, fixed device to track a dynamic, moving biological system. The human body is designed for three-dimensional, continuous motion.
And you're trying to force it into this tiny little window.
You are. And when you do that, you get what I call the twin technical failure points of fixed fluoroscopy. First, motion blur. A fixed C-arm just cannot move with the speed or dexterity of the patient's knee or hip. When the patient is walking, the joint features, the bones, the metal, the polyethylene marker, they're all moving relative to the imaging sensor's fixed field of view.
So even with a fast shutter speed?
Even then, if the relative velocity is high enough, the recorded images are highly susceptible to blurring.
I'm just picturing a streak of metal where the tibial tray should be. And that completely destroys the data you need for kinematics. You need sub-millimeter precision to match that 2D image back to the 3D model.
Absolutely. If you can't locate the precise edge of your implant component down to the micron level in the image, your entire kinematic calculation is useless. It's garbage in, garbage out.
Okay, so that's failure one, motion blur.
Second, and just as frustrating, is the limited field of view, the FOV. The imaging sensor is fixed, and it typically limits your view to a very small window. So if a patient takes a slightly longer step, or if the knee translates just 5 centimeters more anteriorly than you anticipated during the stance phase,
You lose the joint.
you lose the joint entirely. You miss the very peak of the loading cycle, which is often the most desired aspect of the joint mechanics. You've missed the whole point of the experiment.
So you miss the maximum stress point, rendering all the data you did capture incomplete or worse, not representative of the joint's actual performance envelope.
Exactly. And we tried to cheat this for years. I remember when we first started trying to get dynamic data back in the late 90s, early 2000s, we used human operators.
You kidding?
No, I'm not. We would literally strap harnesses onto the C-arm and have 2 very strong, very bored technicians, or God forbid, junior residents on either side, trying to manually maneuver the unit to approximately follow the subject's motion as they walked.
Oh, that sounds absolutely miserable, doctor. And the inherent human error must have been just staggering.
It was a disaster. I remember one specific study where we were trying to track patients doing a high-step gait cycle on a treadmill. We had 3 residents tracking the C-arm. They were trying their absolute best, tracking a knee joint that needed to be kept central at a theoretical speed of 87 frames per second.
And the result?
We ended up with maybe 3 usable, continuous gait cycles out of 50 attempts. The rest were just plagued by sudden loss of FOV, motion blur from inconsistent tracking speed, and massive noise.
And that kind of noisy, truncated data completely invalidates the complex inverse dynamics calculation you need to do later.
It does. It just proved that asking a human operator to track micron-level joint movement at high velocity is like asking a resident to operate for 48 hours straight and then write a flawless 10,000-word NIH grant proposal.
It's conceptually impossible.
It is. The technical constraints were simply too high for any fixed or manually operated system.
So the technical solution, therefore, had to be a transition to mobile fluoroscopy. The core objective was fundamentally to relieve those constraints by creating a robotic-type fluoroscope capable of, well, tracking a human subject during natural, unconstrained activities.
And the emphasis there on natural is paramount. We needed to fully engage the subject's musculoskeletal system.
You want them to walk, climb, and maneuver as they would in their daily life, not some constrained, hesitant, walking for the X-ray machine gait.
Exactly.
And that's the engineering demand then. This requires the machine itself to have kinematic capabilities, range of motion, speeds, and accelerations that are completely consistent with normal human movements. This is not static machinery. This demands true, dynamic, robotic precision.
To really understand the TFS, we have to first define the mobile fluoroscope as a robot in the classic industrial sense. It's a machine built using sophisticated sensors, high-speed computer controls, motor actuators, and very robust mechanical structures.
When we think of industrial robots, I think of the automotive industry. You know, these massive robotic arms spot welding a car chassis. They're incredibly precise, but their mission is to position a tool at a fixed point in 3D space, which is relatively simple.
It is relatively simple. The mobile fluoroscope, however, has a vastly more demanding mission. It's not positioning a tool, it's dynamically aligning the line of sight. That's the axis connecting the X-ray source and the image sensor on the skeletal joint of interest.
And it has to do this while the target is moving through complex, nonlinear, and, frankly, unpredictable human motion.
Yes. The speeds and accelerations involved make this a technical challenge far exceeding standard industrial robotics applications. It's a whole different level of complexity.
And the specific success story here, the one that really turned all this theory into reliable hardware, is the tracking fluoroscope system, the TFS, specifically the second generation TFS-2, developed at the University of Tennessee, Knoxville.
The TFS-2 is a proven system now. It's referenced explicitly in the sources as a patented design. I think it's U.S. patent 8,406,845B2, which was granted back in March 2013. The development effort started around 2007.
So this wasn't just a one-off prototype?
Not at all. It's a dedicated clinical tool that has been used extensively and successfully in hip and knee TJR clinical studies all over the world.
What immediately strikes me about the design is the focus on untethered mobility. It's battery-powered and completely self-contained. Why was being untethered without cords such a critical design feature?
Patient safety and freedom of movement. Tethers are trip hazards, first and foremost. They immediately constrain the environment and they limit the subject's natural movement range. By being battery-powered and untethered, The TFS2 allows for genuine, unrestricted, straight-line gait analysis over significant distances.
Which gives us those natural kinetics we desperately need.
Exactly.
And it's not just untethered, it's omnidirectional. It can move and navigate in any direction, which is something we'll see later is absolutely critical for accommodating the different imaging requirements of the hip versus the knee.
Correct. And despite its complexity, it was engineered for clinical practicality. It's portable and modular, designed so that all its components can be transported through conventional doorways. It has the portability of standard mobile diagnostic equipment, but with the tracking complexity of a specialized research robot.
And while this robot is moving and tracking this torrent of complex diagnostic data, the X-ray frames, the laser distance readings, the actuator positions, it's all transmitted using a dedicated wireless local area data network. The real-time data handling required is just phenomenal.
It's immense.
If you look at the conceptual diagram, figure 26.1, you can clearly see the integrated nature of the systems. The massive mobile base, the dual laser scanners feeding data, the centralized computer controls, and the dynamically positioned X-ray source and sensor. It is a fully orchestrated system working in milliseconds.
To achieve dynamic tracking of a walking subject, the TFS has to execute two fundamentally distinct but perfectly coordinated functions at the same time.
So two brains working at once.
Pretty much. Let's break down straight-line walking. Function 1 is how the system follows the subject's overall movement. This is the large-scale tracking.
Okay, how does it do that?
We call that total body motion tracking, or tracking the torso aggregate. The system achieves this by using dual laser range scanners that are strategically positioned to sense the distance and the contour of the patient's upper torso.
Think of it as the cruise control for the entire mobile base.
That's a good way to put it. The laser scanners are providing the continuous dynamic input for the centralized computer control system.
And the computer uses that data to modulate the speed and direction of the main platform drive motors.
Right. It keeps the distance between the TFS and the subject constant as they walk. And what's more, the dual laser profile provides a subtle contour of the torso. So if the patient begins to shift their weight or rotate slightly, the computer can use that profile change to infer turning direction, left or right, even during straight-line walking.
So the robot handles the large translational movements, maintaining distance and overall direction. Function 2 then has to address the highly localized, high-speed movement of the specific joint we are imaging relative to the torso.
And this is relative joint motion tracking, and this is where the precision engineering really shines. The leg moves massively relative to the center of mass during gait. This localized relative motion is accommodated by high-speed vertical and horizontal servo actuators located within the side wings.
So we have the X-ray generator on one wing and the high-resolution solid-state flat panel imaging sensor on the opposite wing. And these two actuator systems are mechanically and electronically slaved together.
They absolutely have to be. The entire point is to maintain a perfect, consistent line of sight. That means the axis of the X-ray beam must always be aligned perfectly with the center of the imaging sensor, regardless of the relative motion of the knee.
And the constraint here is the sheer magnitude of movement the actuators must accommodate. This isn't arbitrary, right? It's driven by detailed anthropometry datasets. What exactly are these datasets and why are they so critical to the design?
Anthropometry datasets are comprehensive measurements of human body size and movement, often derived from military, ergonomic, or occupational health studies. These datasets tell the engineers the minimum and maximum envelopes of human motion.
So you had to design the robot to handle the 95th percentile of human gait.
Essentially, yes. We looked at the key numbers. During walking, the leg segment as a whole can exhibit a horizontal range of movement up to a full meter, depending on the person's height, stride length, and walking speed.
That's the gross motion the main mobile platform has to handle.
Right. But the joint motion relative to the pelvis is much tighter, and this is the window the side wing actuators must manage. This is the critical engineering challenge.
So what are those numbers?
For the knee, the vertical motion, the sort of bounce as the foot loads and unloads, is typically in the range of 4 to 8 centimeters. However, the horizontal motion, the forward and backward translation of the joint as the leg swings, is much larger, ranging from 7 to 12 centimeters.
And the hip?
The hip, being closer to the center of rotation, has the smallest motion envelope, only a few centimeters in both axes. To design the servo actuators, we had to model for that 12-centimeter maximum horizontal relative motion at the knee. That range dictates the massive acceleration requirements of the side wings.
So if the system can track the massive 1-meter body movement and simultaneously track that critical, localized 12-centimeter relative joint movement with precision, that's when we achieve the desired outcome.
That's the ride-along experience.
The ride-along experience. I like that.
When this dual-function tracking is executed flawlessly, the resulting fluoroscope image stream is stunning. The knee joint or hip joint appears fixed, almost motionless, directly in the center of the image. The entire environment is moving around it, but the joint stays centered.
Meanwhile, the bone segments, the femur and tibia, are moving dynamically and articulating according to the patient's natural gait, completing multiple gait cycles without ever leaving the FOV or suffering motion blur.
You are essentially riding along with the joint, capturing continuous, crystal-clear articulation across the entire range of motion.
Which is something those old fixed C-arms could never, ever deliver.
Not even close.
Achieving that perfect, dynamic, millisecond by millisecond alignment requires extremely advanced control systems. You can't rely on pre-programmed trajectories because every person's gait is slightly different.
No, it has to be a closed-loop feedback system.
And the preferred method for tracking the specific joint location is called visual servoing.
What's fascinating here is that visual servoing allows for markerless tracking. This is a huge step forward in efficiency and accuracy because we don't have to worry about external reference points, which might shift on the skin or require invasive pinning to track the joint.
So walk us through how that vision system actually works. How does the computer identify the implant component geometry without any external markers?
Well, the beauty is that we already know the 3D geometry of the implant. The manufacturer provides the CAD model. The visual servoing system uses sophisticated computer image processing algorithms that are trained to identify the exact location of the joint components, the edges and features of the metallic implants, within each fluoroscope image frame.
So it's essentially matching the known CAD geometry to the image contrast edges, determining the precise position of the implant in 2D space.
That's it. And it does this extremely fast.
We're talking about incredible frame rates here, Doctor. What kind of acquisition speed did the team achieve with the TFS2 that allows for that millisecond level correction?
The TFS2 fluoroscope is capable of providing images up to 87 frames per second.
87.
To give you context, standard video is 30 fps. This is nearly 3 times faster. This means the visual servoing control system is analyzing the image, calculating the position error, and issuing new commands to the servo actuators on the side wings as frequently as every 12 milliseconds.
12 milliseconds. That is just astonishing speed. Why is that specific high-speed feedback loop so clinically necessary?
Because critical biomechanical events happen incredibly fast. Consider the heel strike and load-bearing phase during walking. A patient's subtle shift in balance, or a micro-event like a spike in force during the push-off phase, happens in under 50 milliseconds.
So if your system corrects slower than that,
you miss it. You miss the peak dynamic load that causes micropitting in the polyethylene or reveals subtle implant instability. That 12 millisecond correction speed allows us to capture the articulation geometry at the precise point of maximum loading,
which effectively ensures the implant is never allowed to drift out of focus or out of the FOV during the most dynamically important phases of movement.
That's the goal. Now, of course, there are contingencies. Visual servoing requires excellent image quality and contrast for reliable results.
Okay, so if the image contrast isn't ideal, say during hip studies where you have significant soft tissue or high body mass index subjects, the system needs supplemental methods.
Absolutely. When image quality is insufficient, the system switches to backup tracking methods. This might involve using external target markers placed on the skin, which the X-ray system tracks, or in the TFS2, supplemental visual tracking using an additional digital camera that monitors external targets.
So there are redundancies built in.
The system is designed with these 3 joint tracking modes to ensure that virtually any subject can be diagnostically imaged, regardless of their body type or the joint being analyzed.
And once captured, all those high-speed images are stored on the onboard computers and transmitted wirelessly to the control station. It really is an automated, closed-loop diagnostic system.
It is. But we must shift focus now to safety, which is paramount. Since the TFS is an active, massive machine operating in the proximity of a moving, walking subject, the engineering of the safety systems had to be completely independent and fail-safe.
We're dealing with a moving robot that carries a high-powered X-ray source, tracking a human who is actively walking. The risks are pretty obvious.
The TFS is equipped with a fully independent safety monitoring system. This system uses its own set of sensors, often separate from the tracking lasers, to continuously monitor the subject's position relative to the machine frame. We employ multiple levels of redundancy, including software limit switches and collision avoidance sensors that define a hard spatial limit the machine cannot cross.
And it's also monitoring the integrity of the X-ray tracking and power systems themselves.
Of course.
What happens if a trip signal is actuated, either by an automatic fault detection or, manually by the radiation technician or test personnel?
In the event of any malfunction or a breach of the safety envelope, the safety protocol is absolute. The system is instantly and safely de-energized in milliseconds. We cannot risk any accidental collision or unpredictable movement when dealing with dynamic human movement and high-powered radiological machinery.
Looking at the machine itself, which is often shown in figures like 26.2, the front view 26.3, the rear view in 26.4, the side wing and actuators, you really appreciate the robust engineering.
You do.
Figure 26.4 clearly shows the complexity of those side wings and the powerful servo actuators dedicated solely to managing that precise 12-centimeter envelope of relative joint tracking. It's a bio-robot designed to handle the unpredictable chaos of human motion with engineering precision.
That's right. And that design's omnidirectional motion capabilities are not a luxury. They're an absolute necessity because the operational protocols depend entirely on the joint being analyzed and the required X-ray projection axis.
Okay, let's start with the knee and ankle. They're both typically imaged using a standard mediolateral X-ray exposure. Why is that exposure orientation the preferred standard for lower extremity joints?
Mediolateral is ideal because it gives us a clean, unobstructed view of the articulation profile, how the femoral condyles roll and slide on the tibial plateau. Crucially, the best image quality, minimizing geometric distortion and magnification, is obtained when the joint of interest is positioned as close as possible to the imaging sensor or the detector.
So the patient needs to be on the detector side, not the X-ray source side. And this is what dictates the direction the machine has to track.
Precisely. This creates a sort of directional paradox. If we look at the configuration, like in figure 26.4, when imaging the patient's left knee, the subject must walk away from the central robot base to keep the left knee adjacent to the detector.
Okay, and for the right knee?
Conversely, when imaging the right knee, the subject must walk into the machine, keeping the right knee adjacent to the detector.
Meaning the TFS has to track the subject moving in completely opposite directions for the left versus the right knee, even for the same basic activity like straight line walking.
That's exactly why the omnidirectional base and the dual function tracking are so essential. The right and left ankles follow the identical positional pattern. We require that instant 180-degree reversal of tracking direction simply to achieve optimal image quality based on anatomical requirements.
Now, hip imaging is the wrench in the system. The source material notes that hip studies require a completely different projection axis, anteroposterior X-ray exposures. Why the forced change from mediolateral to AP?
It comes down entirely to soft tissue density and dense bone blockage, specifically the pelvis. The hip joint is deep-seated, it's surrounded by massive muscle groups, and critically, it's shielded by the ilium, ischium, and pubic bones of the pelvis.
So if you try a mediolateral view,
you're shooting through several inches of dense pelvic bone, creating massive scatter and rendering the articulation surfaces of the hip replacement implant almost invisible due to artifact. The image is unusable.
The AP view, then, provides the cleanest projection axis through the joint line.
Yes. The anteroposterior view, shooting front to back, provides the clearest window into the acetabular cup and the femoral head articulation, avoiding the densest sections of the pelvis.
And this change in exposure orientation means the TFS2 must translate in directions that are fundamentally 90 degrees to the translation used for knee and ankle testing.
Correct. The machine cannot track fore and aft relative to the X-ray beam anymore. It has to track laterally. This requires the TFS base to shift its entire omnidirectional movement pattern.
And right versus left hip.
Unlike the knee, right and left hip imaging can often be performed with the TFS translating in the same general direction relative to the patient's motion, though the machine retains the flexibility to shift 180 degrees if the protocol demands it. Figures 26.5 and 26.6 clearly illustrate these drastic 90-degree differences in configuration compared to the knee tracking setup.
Beyond just straight-line walking, the versatility of the test environment seems crucial for collecting clinically relevant data, especially related to the failure modes of TJR.
Absolutely. We need to test the limits of the implants. The TFS2 incorporates strategic cutouts in the rear chassis and the side wings specifically to allow us to integrate external test structures.
So we're talking about inserting ramps, chairs, or other specialized walkover structures directly into the test protocol.
This is vital. We can now test kinematics during functional activities that place maximum stress on TJR components, such as rising from a low chair, which is a huge functional challenge for many hip patients, or climbing and descending a ramp.
Simulating activities of daily living that were completely untestable before.
Exactly. Now, while current clinical protocols often stick to straight-line motion, the source material does note that the platform is capable of tracking complex subject motion like turning or changes of direction.
And this opens up entirely new clinical applications.
Indeed. Simple translation tracking is one thing. Tracking rapid rotation, like a patient cutting or pivoting, is far more complex. Rotational forces are often responsible for ligamentous injury and instability. This complex motion tracking capability could revolutionize specialized diagnostics, particularly for high-demand patients in sports and military applications.
Where dynamic stability and rapid directional changes are vital for return to duty or play.
Precisely. And we should also acknowledge parallel research. There's the group at ETH Zurich, for instance, which developed a comparable machine focused on knee tracking during activities like stair descents, proving this field is really maturing globally.
So we have this incredible sophisticated robot that can track joints dynamically. Currently, mobile fluoroscopy serves primarily as a powerful research tool used to refine and validate orthopedic joint implant designs. Where does the next phase of evolution take us?
Well, the immediate path is driven by Moore's law. We can anticipate continued rapid advancements in solid-state electronics, computing power, and sensor technology. This scaling will allow us to achieve even higher resolution images at dramatically faster acquisition rates.
And more speed and better resolution means opening the doors to previously impossible patient maneuvers.
Yes, think of the potential for imaging athletes during extreme motions. Jumps, landings, rapid lateral shuffles, and fast turns. This data high fidelity in vivo kinematics during peak athletic load is essentially non-existent right now. It could be absolutely revolutionary for understanding athletic injury recovery, ligamentous reconstruction stability, and injury prevention post-surgery.
That seems like the logical high-end extension. But what are the radical future research avenues that could truly transform diagnosis for the average patient?
The first major technical leap, which is already in conceptual research, is integrating biplanar fluoroscopy into the existing TFS concept.
Okay, so right now we capture 2D images and we computationally match them to 3D models. That computation is time-consuming.
It is. Biplanar fluoroscopy means using two synchronized X-ray sources and detectors positioned at 90 degrees to each other to view the joint simultaneously from two different planes.
Which would provide direct 3D imaging of the joint during movement.
Exactly. Think of it as generating a 3D movie of the articulation in real time. This capability would eliminate the computational heavy lifting of 2D to 3D registration, significantly speeding up and enhancing the in vivo analysis workflow. It would allow for immediate feedback on surgical performance.
That's a massive engineering challenge, though. You are essentially putting two massive high-speed tracking systems into close proximity while maintaining safety and precision.
It is. It requires highly accurate synchronization and a significant increase in data handling, but the payoff is immense. Then there's the truly futuristic possibility, leveraging the mobility of the TFS base to create the clinical equivalent of a CT scan.
How would a mobile fluoroscope create a CT equivalent?
By spinning the mobile fluoroscope system around a patient who is standing or fixed in a weight-bearing position, we could acquire comprehensive diagnostic data from 360 degrees, similar to a standard CT, but crucially under functional weight-bearing conditions.
Which could provide unprecedented diagnostic detail for subtle fractures or alignment issues that only manifest under load.
Precisely. And finally, there's the expansion beyond the lower extremity. The source material mentions initial conceptual research regarding shoulder and cervical spine imaging. This sounds like an entirely different beast kinematically.
A whole different ballgame.
It is. The shoulder and cervical spine have a vastly higher degree of 3D motion dexterity and complexity than the knee or hip. Think about the range of motion required for something like a golf swing, or even just reaching across your body. To track that, the current TFS platform, which is designed for translational gait, isn't enough.
You need a smaller, more agile system.
Yes. We would require a supplementary robot manipulator, a smaller, high-dexterity robotic arm equipped with a miniaturized X-ray source and detector pair. This supplementary robot would handle the high 3D motion dexterity common to the upper body. It would work in tandem with the main TFS platform, which might still provide the overall stability and body tracking.
If we can achieve that level of tracking for the shoulder complex, the glenohumeral and scapulothoracic rhythm. It would open shoulder arthroplasty to the same level of detail. In vivo study we now perform on knees and hips.
And considering how complex and stability-dependent shoulder mechanics are, that data would be transformational. The ultimate clinical utility, then, is this. We are no longer evaluating implant designs or surgical techniques based on simplified controlled lab studies or fixed post-op x-rays.
We are getting the data points that truly matter, the force vectors, the microinstabilities, and the component wear patterns generated under the duress of a fully engaged dynamic musculoskeletal system.
This profound new insight feeds directly into better design, more accurate preoperative planning, and ultimately far superior longevity and quality of life for our TJR patients. It validates our work by showing us the outcome in its most critical context: life in motion.
It's just astonishing to consider the rapid progress. In just over a decade, we've moved from manually pushing a fixed C-arm around and throwing out noisy data sets to having a patented, sophisticated, omnidirectional robot capable of routine, continuous, high-speed in vivo studies of implants during completely normal activities.
The resulting test protocols are infinitely more realistic, more complex, and thus more valuable to the biomechanical and clinical community. This technology underscores the simple truth that we can't fully evaluate a mechanical repair until we observe it operating under the duress of life, not just the constraints of a passive X-ray machine.
That dynamic validation is the new gold standard.
Indeed. Now, for you, the learner, to consider as you process this deep dive, we focused heavily on total joint replacement performance and polyethylene wear. But if tracking capabilities continue to improve, especially moving toward biplanar 3D imaging and handling complex high-speed movements like jumping and turning what specific non-TJR orthopedic injury, perhaps one related to chronic microinstability of the ankle, or a subtle anterior cruciate ligament laxity, could be best diagnosed by observing it under the continuous high-speed observation of a mobile fluoroscope.
And more importantly,
what specific ligament reconstruction or fracture fixation technique would you want to validate using this ride-along data that shows the joint operating at its absolute functional limit?
Food for thought as the fields of orthopedics and robotics continue their fascinating convergence.